Hey guys, thanks for watching. In this video we're going to be going over part 2 of the week 12 concepts for Physics 111. So starting off with work on a gas, if we remember back to when we learned about work initially, we know that work is going to be equal to our force times our displacement, assuming that that force is parallel to our displacement. And we can see in this little image over here, if we were to have a scenario where we have force applied to a piston compressing a gas, it would look something like this, and basically our force is going in this direction, and here is our gas basically that's being compressed by this force. And we can then define this work on a gas as work being equal to our negative pressure times our change in volume. And this brings us into the first law of thermodynamics, which states that if a system undergoes any changes, then the change in internal energy is given by change in U equals Q plus W. And our change in U is going to be the change in internal energy, Q is going to be our energy transferred by heat, and then W is going to be the work done on the system. So I believe in the textbook it defines W as being the work done by the system, so in this case you would want to use a negative sign, but we're going to be using this equation here where we define W as work done on the system. So positive work would be work going into the system, and negative work would be work being done by the system. Thermal processes, we have isobaric processes which would have constant pressure, isothermal would have a constant temperature, isovolumetric or isochoric would have constant volume, and adiabatic would have no heat added or removed from the system. Alright, next we're going to be talking about heat engines and thermal pumps. So starting off with heat engines, these are going to take energy in the form of heat from a hot reservoir, and they're going to convert some of that energy to work. And the remaining energy and heat is going to be put into a cold reservoir. And examples of this would be a combustion engine or maybe coal burning at a power plant. And it's just important to realize that not all the heat can be converted to work. So let's take a look at this diagram here of a heat engine. So we take energy in the form of heat up here from this hot reservoir, and it's going to move down into our engine, and the engine is going to use that heat in order to put out some form of work, usually mechanical, and basically whatever heat is left over from our hot reservoir or whatever energy didn't get converted is going to go down into this cold reservoir. And this brings us into the efficiency of a heat engine. Basically, like we stated up here, not all the heat is going to be converted to work. So we want to know how efficient this engine is at converting heat to work, and we can use these equations here. Basically, we're going to take the work done by the engine and divide by the heat input. We want to know how much work we get out compared to how much heat or energy we have to put into the heat engine. And then for thermal pumps, it's basically the opposite of a heat engine. We're going to take work from an outside source, so normally electricity, and that work is going to go into the engine, and we're going to use that work to move heat from a cold reservoir into a hot reservoir. And this is against the natural flow, and the excess heat which was removed and energy which wasn't used is also going to go into that hot reservoir. And examples of this would be a refrigerator or an air conditioner and heat pumps. And basically, just to kind of explain with maybe a refrigerator, the actual inside of a refrigerator would be this cold reservoir, right? That's what we want to get cold. And basically, using electricity, we're going to pump as much heat out of this inside of the refrigerator, and that heat is going to actually get pumped directly into our house, basically, or wherever we have our refrigerator. Basically, we just want that hot air out of the cold reservoir, and we want to get this section here as cold as possible. And this brings us into the coefficient of performance, or COP, and this is the ratio of the useful output to the work input. And for a refrigerator or an air conditioner, we're going to define that as being basically the amount of heat we got out of the cold reservoir divided by the amount of work we put in to get that heat out of there. And our values are going to usually be between 2 and 6. And then for a heat pump, which is basically, if we think of our air conditioner, when we're in the winter, we're not gonna turn on the AC. Well, maybe in Arizona, but normally we would want to turn on the heater. And basically, this just reverses the process where we want the inside of our house to be the hot reservoir rather than the cold reservoir. And in order to find the coefficient of performance for a heat pump, we're going to take the amount of heat which we are able to move into the hot reservoir over the amount of work it takes to do that. And our values are going to be between 2 and 4. All right, now we're just going to end by wrapping up the second and third laws of thermodynamics. The second law states that no heat engine operating in a cycle can absorb energy from a hot reservoir and use it entirely for the performance of an equal amount of work. So basically, like we had already stated earlier when we went over heat engines, that all that heat that we're putting in to the engine is not going to all get converted into work. Some of that has to go into the cold reservoir. And basically what we have to realize here is that heat engines cannot be 100% efficient. And that brings us into entropy, which we denote as a capital S, and this is going to describe the disorder of a system. So basically our change in entropy is going to be equal to our heat over our temperature. And now we can rewrite that second law of thermodynamics to state that the entropy of the universe is increasing at all natural processes. And basically, even when we have a system which seems to be becoming more ordered, when we look at that from a kind of a bigger view, we're going to see that the entropy of the universe, however, is always going to be increasing within these natural processes. And the third law of thermodynamics states that it is impossible to reach a temperature of absolute zero. So thinking back to part 1 of this concept, we were talking about constant pressure thermometers and constant temperature thermometers, and basically in those scenarios when we would extrapolate the plots, we saw that at absolute zero or negative 273.15 degrees Celsius, we would reach, for instance, zero pressure or zero volume. And basically that's theoretical. If we were to reach an absolute zero, that would be the case. However, we know that it is actually impossible to reach that temperature of absolute zero. All right, that's going to wrap it up for this video, guys. Thanks for watching.